So today we'll discuss first the static pressure. If we have a tank of some liquid, let us consider a column here where the pressure is P0 here and the pressure is P here. There are also pressures from the side. For a liquid, the pressure is always perpendicular to the surface. So if we only consider the vertical forces, we have P0, we have the gravitational force, and we have the pressure from the bottom. The gravitational force is equal to the total weight. So if the area is the unit area, or let's say that the area is A. P0A is the total force exerted on the top surface. PA is the total force exerted on the bottom surface. The height of this column is supposed to be h. So the volume is h times A. The volume times the density is the mass. That times g is the weight, is the total force. So this has to balance because it's a static situation. So we have P is equal to P0 plus rho hg. And this is equation 15-8. So therefore we know the pressure at the depth of h is equal to the top pressure, which is usually 1 atmosphere, plus rho gh. So in a swimming pool, the pressure at the bottom of the swimming pool is much higher than the pressure on top. Does anybody know at what depth would the pressure be 2 atmospheres? It's about 10 meters. For water, the density is equal to 1 gram per cc. And you put that in, it's about 10 meters. So after 10 meters of water, the pressure would increase by 1 atmosphere. Now, the way we have drawn it is a rectangular arrangement. But suppose suppose we have a water this way. Then when we talk about the pressure here, that pressure is increased by rho gh, and that is h. So remember, h is always the vertical distance. You don't take this oblique distance. Is that clear to everybody? Now let's look at the problem 15-3. If you have a U-shaped tube where is water on this side and it's oil in here, this area is oil. So let us ask, for example, how different are these two levels. To find that, first, if I do this, the pressure at these 2 points are the same. You can apply this formula. The pressure at this point and the pressure at this point, the P0 cancel each other. The rho GH is the same. So the pressure at this point is the same as the pressure at this point. But the pressure at this point, since this is water, so the pressure at this point, let's say call it B, is equal to atmospheric pressure plus rho water G times this distance, H1. But the pressure at B is equal to the pressure at C. And the pressure at C is equal to P0 plus rho oil times GH2, where this distance is H2. H2 is the height of the oil. So, since these two are the same, so we get rho W H1 is equal to rho oil H2. Since rho W, the water density is higher than the oil density. This is higher than this, so H1 is less than H2, and that's precisely what would happen. Pascal principle, and that's the principle of a hydraulic lever. A hydraulic lever is a very common arrangement. You have a small tube here, you have a big area here. And it's all liquid underneath. If these two are the same height, the pressure is the same. So if I apply a pressure here, P, then that's the same pressure here. But if the area here is A, the area here is A prime, then the total weight here this weight or this weight is P A prime G. If A prime is very large, the total pressure here is PAG, and that ratio is equal to A prime over A. Sorry, no G. Because of the two pressures are the same, so therefore the forces are proportional to the area. And if this area is very large, you have a very large area. So that's the hydraulic brakes all follow this principle. You have a small tube, you exert a pressure on it, and then it can sustain a very large weight. But of course, if you do work on it, then if you press this down by 1 inch, if this area is very large, this displacement is very small. So you gain by having a much larger force, but you have to press a large distance. If you want to do any work, then you have to press a large distance and raise this side by a small distance. So you don't gain in any work, but you gain in any force. Does everybody understand this point? So the hydraulic pressure is not one for which you magnify the work. You can magnify the work because there's conservation of energy. But what you can magnify is the force. Next, we talk about the Archimedes principle. Please read this. I'm sure you have all learned this in high school. Steady flow motion is called also called laminar flow. Laminar 的意思是层一层一层的。So, 假如 if you have a tube， 像一个水管子 ，if you apply pressure on the side, then the water would flow inside, but the water near the surface would flow with a zero velocity because there's friction. The contact with the tube would slow down the water, but the water in the center would flow rapidly. So if you plot the velocity, this is the tube, you would get a velocity which looks like this. The water in the center flows fastest. The water on the edge flows slowest. So you can think of the flow as many layers. Each layer is a tube, and the center tube would be flowing fastest. And that is a typical laminar flow. However, if you now apply much larger pressure, then it will move faster and faster. And when it reaches a certain speed, it becomes turbulent. So you can go from a laminar flow to a turbulent flow. This is a very complicated subject, but it is an extremely important subject because it has tremendous applications. Not only is it important for the water company. The water company has to pay attention to this. If they apply too much pressure, it will become turbulent. When it becomes, you know what the turbulent flow is like. If you, in fact, when water comes out of the faucet, if it goes too fast, it becomes turbulent. It becomes 乱。中国叫做喘流。A famous problem was the problem of at what pressure difference or at what speed at the center would a flow go from laminar flow to a turbulent flow. This is one of the famous problems, and this problem is still being investigated today. But Professor C.C. Lin of the center was one of the early important contributors to the field. What happened was that in the 1920s, Heisenberg, the famous Heisenberg, the one who started the quantum mechanics, in writing his PhD thesis, wrote about this problem. He was a student of Sommerfeld in Germany. They were both Germans. And Heisenberg did not write a thesis on quantum mechanics. He wrote a thesis on turbulent flow. And he got his PhD, and then he went on to become a great founder of quantum mechanics. But his PhD thesis was under dispute about whether his theory of the change from laminar flow to turbulent flow was correct. And then some 20 years later, C.C. Lin, then a graduate student, wrote his thesis, which clarified the situation, and in some sense it mostly supported Heisenberg's work. Both Heisenberg's work and C.C. Lin's work were very important at the time. And Lin later became a very distinguished professor at MIT. He's now a professor at the center in清华. The turbulent flow is especially important because of the airplane industry. When an airplane flies very fast, there's turbulence near the airplane, especially under the wings. And that turbulence creates an energy drag because the turbulent flow consumes energy. So therefore, in order to save fuel, you have to understand the theory of turbulent flow. So it is a very important subject. And in departments of aerodynamics, turbulent flow is one of the most important subjects. Equation of continuity. If you have a tube where this can be a tube inside a big tube. So what I'm drawing are the lines of flow. It could be in a very big tube. If this area is A and this area is A prime, and we are talking about a incomprehensible flow. An incompressible flow. Incompressible 就是不可以压缩的，换一句话说就是密度不可以改的。比如说是空气。是一个 compressible flow， 因为空气你压力的话，你加压力的话，它就变得密度比较大了。But water is essentially incompressible。你要加很大的压力 ，water 的 density 才会有很小的 change。So mostly talking about the water is a incompressible flow。那么我们现在 talk about 一个 incompressible flow。那么，假如这是个A 然后这儿的 velocity 是 v， 这儿的 velocity v prime。那很显然a times v times delta t in a time delta t you would have a distance of v delta t times an area. So you get this is the total volume of liquid that enters this area. And that must be equal to the amount which goes out, because you cannot compress it. So therefore, this is equal to a prime v prime delta t. So av is equal to a prime v prime. In other words, the velocity is inversely proportional to the area. That's of course obvious. If you have a river which is very narrow and suddenly becomes very wide, then the fast flow in the narrow part, upon coming to the wide part, would slow down, obviously. Bernoulli was a very distinguished family. That family produced a number of important mathematicians and scientists. There is a chapter about the Bernoulli family in the book that I had recommended to you, called The Man of Mathematics. And the Bernoulli's equation is something like this. Suppose you have this is the y-axis, this is a vertical, upwards. Suppose you have a tube which goes this way. Let us consider a flow which goes this way. And we already know that the area here is smaller, the area here is larger, so therefore the velocity here is larger than the velocity here. So let us say after a delta t, this plane goes to here. So it goes from the solid line to the dotted line. Now we want to consider energy conservation. Again, these are not necessarily, we are not thinking of it as a tube. These are the lines of flow. So the whole thing may be in a very big vessel. And but there's a laminar flow, so they are flowing smoothly. So at this point, there is an area there's A1 and here is A2. At this point, there's pressure 1, there's a pressure 2. At this point, there's V1, there's V2. Now we know A1 V1 is equal to A2 V2. We already had that. What does energy conservation says? Energy conservation says that the work done on the water in this region is equal to the energy increase. Right? That's what is meant by energy conservation. We are assuming there's no turbulence. So there's energy conservation. But what is the work done on this? This is equal to, in this side, we do work on it. And the force is equal to P1A1. That's the force. The distance traveled is equal to V1 delta T. Right? This is the force done on the system. But at this point, the system does work on the outside. So therefore you have to subtract P2A2. P2A2 is the force times the distance traveled. It's V2 delta T. So this difference is the total work done on this system. Now, what is this one? What is the energy increase? The energy increase is the energy in the middle is not changed. Before delta T and after delta T is the same. The material may have changed, but it's the same amount of mass moving with the same velocity at every point. So there is no change. The only change is that in this area and in this area, or in this volume and in this volume. So what is the change? The change is the total. What is the total mass of it? It's A1 V1 delta T. That is the volume times rho. That's the total mass. The total mass times 1/2 V1 squared minus V2 squared. V2 squared minus V1 squared. That's the kinetic energy change. Does everybody agree? This part is the mass. 1/2 m v squared is the kinetic energy. So this part is the kinetic energy here, and this part is the kinetic energy here. And so it's the kinetic energy increase is that, plus the potential energy increase. The potential energy increase is the same thing. It's the same mass plus it's the rho gh or it's mgh. So g times y2 minus y1. In the bracket, here's the kinetic energy increase, here's the potential energy increase. So let's write it out. We have now delta V. Let's write V. The volume is equal to A1V1 delta T, and it's equal to A2 V2 delta T. So if I rewrite this equation, I get P1 times V1 times this capital V times V1 times capital V. No. The P1 capital V minus P2 capital V is the left side. Is equal to rho v times 1/2 v2 squared minus v1 squared plus g y2 minus g y1. So if you cancel the v, you get the p1 minus p2 is equal to rho 1/2 rho v2 squared minus v1 squared plus rho g y2 minus y1. Or you get p1 plus 1/2 rho v1 squared plus rho g y1 is equal to p2 plus 1/2 rho v2 squared plus rho g y2. That's called the Bernoulli's equation. That's 15-20. This is a very useful formula. For example, let us take if you have a tank of water and you have a little hole near the bottom, then everybody would know that the water would flow out. This is a sample problem. (15-9). So let us apply. We assume that this is a smooth flowing. If it is too large a height, it could become turbulent. But let us have a not too large height. So suppose this drop of height is h. So we take this point to be 1, take this point to be 2. At 1 there's the atmospheric pressure plus the original velocity at 1/2 rho v1 squared. But if this is a very small hole, the surface drops down very slowly, so we neglect this. Plus rho g h is equal to the pressure at this point is rho 0, is p0, again atmospheric pressure, plus 1/2 rho v2 squared plus 0. So since p0 cancels p0, we get the rho gh is equal to 1/2 rho v2 squared. Which essentially says that the velocity is equivalent to if the thing has to drop down from here to here. But that's not strange, because by energy because we obtained this formula through the Bernoulli's equation. The Bernoulli's equation is based on energy conservation, and so therefore, of course, we get energy conservation. I advise you to read chapter 15 very carefully. There are a lot of little discussions. I think you gain general information by reading the book. But as far as the physics principles are concerned, we have in the last 40 minutes have gone through the important points completely. So we now go to the next chapter. Chapter 16, oscillations. Everybody knows that if you have oscillation, there is a frequency. There's a unit which is called a hertz. 1 hertz is equal to 1 cycle per second. And if you have a clock, the pendulum usually has a frequency of 1 hertz, 1 cycle per second. When you talk about cycle, it has to return to the original point. If you have a swing, usually the frequency is, let's say, 1/3 of a hertz. But for radio waves, it has a very high frequency. If you go to light waves, light has been known, of course, by mankind since the beginning of history. But it was only after Maxwell that it was recognized that ordinary light, visible light, is a electromagnetic vibration, and that has a very, very high frequency, much higher than, say, radio waves frequency. And later on, people found the gamma rays. Gamma rays have even higher frequencies. Now, if you look at the figure 34.1, of the book, it has a spectrum of various vibrations. These different vibrations go from very slow ones to very, very high frequencies. The highest frequencies are gamma rays or hard gamma rays or cosmic rays. Cosmic rays, some of them have enormously high frequencies. So oscillation is a very fundamental phenomenon. It's a very very common. Now, in the book, it writes a typical one-dimensional oscillation. The displacement x as a function of t is written as x0 times cosine omega t plus phi. This x0 is called amplitude. 中文叫振幅. This omega is called angular frequency. Angular velocity. This phi is called phase angle or phase constant. Or phase constant. And this, what's under the cosine, the whole thing is called the phase. The phase would usually go from 0 to 360 degrees to 720 degrees, and so on and so forth. That the phase is the most important thing was well known once people began to study, for example, water waves. But we now know in the 20th century that the concept of phase is deeply related the concept of phase is related to the mathematical structure of the fundamental forces of nature. There are many fundamental forces of nature. I'm sure you know the gravitational force is a fundamental force of nature. Electric and magnetic force is another type of fundamental force of fundamental forces of nature. Then in the 20th century, we know that there are additional forces. There are the so-called strong forces, which determine the structure of nuclei. There are the weak forces, which determine, for example, radioactivity. So in the 20th century, we now know that there are 4 types of forces. It turns out that all these forces are related to the concept of phase. And in fact, the prevalent theory now is called gauge theory.中国叫做规范理论。The structure of all these 4 fundamental forces of nature are all gauge theories. But gauge theory is a wrong name. 这英文有一个字叫做 misnomer。Normal 的意思就是讲命名 ，mis 是错误 ，misnomer 的意思是一个错误的命名，根本当初不应该叫 gauge theory， 应该叫 phase theory。因为它的基本的观念是 based on the concept of phase。我在今年的年初I gave a talk in Germany, in Ulm. Ulm is the small town where Einstein was born 125 years ago. They had a celebration for the 125th birthday of Einstein. And I gave a talk there in which I talked about the fundamental contributions of Einstein. And in that talk I mentioned that what Einstein wanted to do was to understand the structures of all forces, and he wanted to have a unified understanding, 叫做联合统一场论。那么 he did not succeed in his lifetime. We have not succeeded yet, but we know that one of the key ingredients of the future unified field theory is gauge theory, or in fact phase theory. So that shows that the concept of phase is of fundamental importance in physics. Now, the equation that gives rise to the phase is, of course, the simple equation. This equation we have written down several times, and we have applied it to a pendulum, we have applied it to a mass attached to a spring. But in those discussions, we did not discuss dissipation. in those examples that we discussed, either a simple swing or a compressed swing, there was energy conservation. But in actual practice, all motion encounter frictions. And in particular, you can do an experiment. And the diagram of the experiment is given in the book. It's suppose you have a spring here, you attach a mass to it, but you now produce some larger friction than given by air. So, for example, you have an arrangement like this. You attach an object to the mass and then immerse that object in some liquid. So when the mass moves up and down, this object moves in the liquid and creates a friction. So this way you can study the dissipation. And it turns out that the dissipation follows an equation such that mx double dot is equal to minus kx minus bx dot, minus bx dot. X dot is, of course, the velocity. It gives you a force which is proportional to the velocity. So this is the typical harmonic motion with dissipation, and is usually written in this form. Harmonic motion with dissipation. Why do we call it the dissipation? Let us try to look at the energy balance of this equation. We have looked at harmonic motion before, and we have written the conservation energy equation. How did we obtain that? We take this force equation and multiply by x dot, by velocity. So we now do the same. We get m x double dot x dot is equal to minus k x x dot minus b x dot squared. But this is equal to ddt of 1/2 mx dot squared is equal to minus ddt of 1/2 kx squared minus b x dot squared, or is ddt of the kinetic energy, that's this term, plus potential energy, that's this term, is equal to minus b x squared. So the total energy, that's the sum of the kinetic plus potential energies, the total energy changes with time and is always negative, minus bx squared, minus bx dot squared. And that's why this is called dissipation. It's a dv squared. It's proportional to the velocity squared. That also shows that B has to be positive. Because dissipation always decreases the total energy, decreases the total mechanical energy. Actually, later on we learn that the total, if you include the heat energy, then what is lost in the mechanical energy goes into heat. So once you understand that, you eventually find out that if you add the heat energy, then the total energy is not changed. What happens is that you are changing the mechanical energy into heat energy. And after that is understood, people ask, can I change heat energy back into mechanical energy? Answer, no. And that is the second law of thermodynamics. We'll come to that. So the simple statement of the second law of thermodynamics is that you can change mechanical energy by various means, by friction, into heat energy. But you cannot net change a heat energy into mechanical energy. Okay, now we want to deal with the mathematics of this boxed equation, the harmonic motion with dissipation. This equation is a second order linear homogeneous differential equation. Second order because you have the second derivative. Linear because everything is either x or x dot or x. It's only the first power. Homogeneous in the sense that every term is the same order. If you have something on the right hand side which is not proportional to x, then it's not homogeneous. So this is called homogeneous linear differential equation of second order. For such homogeneous differential equations, there's a trick. The trick is depends on the fact that an exponential function, let's take exponential I alpha t. If I differentiate an exponential function, I get the same exponential function multiplied by constant. So if you repeatedly differentiate it, you do not get new functions. You only get the same function multiplied by different constants. And that is the way to solve such an equation. So we try a solution. We try x is equal to x0 times exponential I alpha t. How do I know I should try this? I just said that because when I differentiate, I get this back the same. If I start with let's say x to the fifth power, if I differentiate it, it becomes x to the fourth power, and that's not the same as the original one. So that's very bad for trying to solve this equation. But the exponential has the property that it doesn't change form. It only becomes multiplied by something. So if I substitute that into this equation, into the original equation, I get mx0 times exponential I alpha t. The second derivative becomes I alpha squared. Each time I differentiate, I get I alpha down. And the next one is v. I differentiate once, so I get the 1 I alpha. The last one is k. So do you agree that this is the equation? So that means I get, this is not 0, so this has to be equal to 0. So I get minus alpha squared plus I b alpha plus k is equal to 0. no more x. So that determines alpha. So this is a quadratic equation, so we get alpha is equal to, m, and this is wrong. Minus m. So it's equal to 2m IB plus minus square root of minus b squared, or IB squared minus plus 4mk. Let us write that as b over 2m I plus minus omega 0, where omega 0 is equal to square root of 4mk minus b squared divided by 2m. Did I make a mistake? No, correct. So I can take either the plus sign or the minus sign. So let's first take the plus sign. If I take the plus sign, I get x is equal to x0 times exponential exponential I t times b over 2m I plus omega 0. And that, according to what we just did, it's a complex solution, but it is a solution. However, if I take the minus sign, I would get this. But this is equal to x0 times exponential minus b over 2m t times exponential I t omega 0. This one is equal to x0 exponential minus b over 2mt times exponential minus I t omega 0. So I get two solutions. Both of them have a real damping term. This is called damping term. It's an exponentially decreasing function of time. If the coefficient in front of t is small, if b is almost 0, in other words, if it's a very frictionless, almost frictionless motion, then this exponent is very small, and it takes a long time for it to damp down. T has to be very large for that exponential function to die down. So that's called slow damping. But then we have these two exponentials, and these are complex. Now, we have two different solutions. Since the original equation is linear, I can take any coefficient of the first solution, add it to any coefficient of the second solution. I still get a solution because the original equation was linear. So once you understand that, you know what is the real solution. You just take the two of them. For example, if you add them with the same coefficient, you get a cosine. If you subtract them and multiply it by I, you get a sine function. So therefore, what you get in general, these are special solutions. The general solution is a linear combination of the two, and so the general real solution is x equal to sum x0 times the damping factor minus bt over 2m times cosine of omega 0t plus phi. Does everybody understand this last step? Why the sum of these two becomes this? It's trivial, but you have to go through that argument. So to think of it, you have to be totally familiar with why those two special solutions, when you multiply by proper coefficients and add, it comes to this form. This form, this cosine of two things, can be expanded into a cosine term plus a sine term, and each of them can be written as the linear combination of these two, and vice versa. Any real linear combination of those two has to be of this form. Now, if I plot this curve, first I can plot this exponential function. This exponential function goes like this. And when this cosine becomes 1, it touches this curve. When cosine becomes minus 1, it touches the reflected curve. So the x oscillates between these two. So therefore, you get, when t is equal to 0, this term is 1, so you get some phase. So you get something like this. I did very well. It looks pretty good. All oscillations follow this. If you have a very small damping, then you can go on and on and on. The book has a diagram with a much smaller damping than what I had. How do you count the damping? You count the number of oscillations before it goes down by a factor of 2. And this one damps down maybe after 6 cycles. In the book, I think that one has maybe it damps down by a factor of 2 only after maybe 20 cycles. But now one can make oscillations with very, very small damping, such that you can go to billions of oscillations without any real change of the amplitude. what we have done in the previous section is to look at the damped simple harmonic oscillator. That is when we come to electricity, to alternating currents, that becomes a extremely important subject. In fact, the whole electric engineering department used to study only such a type of equations. However, an even more important one is that if the motion is periodically subject to an external force, so that's called forced oscillation. A forced oscillation has an equation like this. But it has something on the every term in here is a force, of course, because m x double dot is a force. Suppose there's a force which is, let's say, cosine omega t plus, let's say, phi 1. This omega is the external frequency. We had omega 0. Omega 0 is the natural frequency. Omega may, this external frequency may or may not be equal to omega 0. So that's called forced oscillation. So we now want to find a solution of this equation. We try. It's clear that learning from what we had done before, we should again use complex variable and only worry about how to add the solutions, add complex solutions to eventually make it real. Why do we do that? Because the exponential function, exponential I alpha t, has the nice property that every time you differentiate, you do not change the form of the equation. So should we try exponential I alpha t? No, because if we try exponential I alpha t, the x double dot is exponential I alpha t, x dot is exponential I alpha t, x is exponential I alpha t, but on the right hand side it's exponential I omega t, and that doesn't work. You get an equation which the left side and the right side do not match. So what should we try? Obviously we should try exponential I omega t, because then every term is I omega t. So we are going to try x equal to x0 exponential I omega t. So we put that in there. Then we get x0 exponential I omega t times m times double dot. I get I omega squared plus d x dot, so I get I omega plus k. That's the left side. And the right side, the original, I told you that we are going to worry about the complexity afterwards. So we now just write f exponential I omega t. So that's a brilliant idea, because both sides have exponential I omega t. So therefore So we get x0 times minus m omega squared plus b I omega plus k is equal to f. No more x. So x0 is equal to f divided by minus f divided by m omega squared minus b I omega plus k. X0 is the amplitude of the oscillation, and the denominator is a complex number. To understand how this complex number looks like, let's call it D defined to be m omega squared minus b I omega plus k. And let us now go back to the k. Now we had the equation before, namely k is equal to m alpha squared minus ib alpha. Previously we had an equation for k. K is equal to m alpha squared minus ib alpha. So I substitute that in there, I get m omega squared minus b I omega plus something's wrong. Just a minute. Did I get a sign wrong? Yeah. Minus m alpha squared plus b I alpha. So that is equal to m omega squared minus alpha squared plus bi or minus bi omega minus alpha. So that is equal to omega minus alpha times m omega plus alpha minus ib. But alpha, by definition, is equal to b over 2m, is the damping factor, plus omega 0. So I substitute that in there. I get omega minus omega 0 minus, there's an I here, minus b over 2m I times m omega plus m omega 0 minus b over 2i plus b over 2 minus ib. Right. Which is equal to omega minus omega 0 minus b over 2m I times m omega plus omega 0 minus ib over 2. let us look at this expression. This expression is the product of two numbers, a complex number and another complex number. Take the case of small damping. I.e., omega is much bigger, b over 2m. If omega is very small and is very large compared to b over 2m, that means the damping, you oscillate. If omega is large and the damping is small, that means you oscillate many, many times before it damps. So let's take that case. If that is the case, you see that this term is small. And that means, we'll come back to that. Here, omega and omega 0, so omega and omega 0 are both large. We consider omega to be near omega 0. That omega is large, omega 0 is also large, but the difference between omega and omega 0 to be small. That difference may be of the same order as this damping term. And here you see this is a large number, this is a small number. So d in that case is equivalent to, is approximately equal to omega minus omega 0 minus b over 2m I. This is a small number, this is a small number, and this IB is essentially 2m omega 0. Because this is small and omega is so equal to, approximately equal to omega 0. So you see that what is this d? If you take the absolute value of d squared, it's equal to omega minus omega 0 squared plus b squared over 4m squared. If I now take the square root of this, and put it in the denominator, the x0 absolute value is equal to f absolute value divided by d absolute value, and that's equal to f absolute value divided by this number. So if I plot omega here and let this point be omega equal to omega 0, then this expression, 1 over this expression, the amplitude is like this. When omega is equal to omega 0, the denominator is smallest, so the amplitude is the largest. And the width here is proportional to this. This curve is given in the book. It's called the resonance curve. So let me put it in words. We have a oscillator which naturally oscillates with a frequency, and that frequency is called omega 0. I now apply an external frequency on it which may or may not be the same as omega 0. Then when the external frequency is very different from the natural frequency, the amplitude is small. But when the external frequency is like the natural frequency, then the amplitude becomes very large. Now this phenomenon we all know. It's if you have a child on a swing, if you periodically give the child a push, if you push with the same frequency as the natural frequency of the swing, then the swing would go higher and higher. But if you just take a very different frequency, then it doesn't. You will not be able to make the thing go higher and higher. And when you build a bridge, for example, the bridge has a natural frequency. In fact, there's several natural frequencies. We'll come to that. Because what we have been doing is a one-dimensional problem. In general, you have a multi-dimensional problem, then there are several ways of vibrating, and they have different frequencies. So it can have more than one natural frequency. If now you apply a force on it, and that force resonates with one of those frequencies, then that mode of vibration will be amplified. And in fact, there was a famous case of a bridge in the United States near Seattle. It's called the Tacoma Bridge. I think it was something like in the 1930s. The engineers did not calculate it correctly. And when the wind reaches a certain speed, it has a driving force with a certain frequency. And it happens that that frequency matches one of the natural frequencies of that bridge. And then it vibrates bigger and bigger. And I think something like a few hours before the disaster was going to happen, they realized, the city realized that something very important is going to happen. So they make the movie of it. They took a real movie. And then you can see that it becomes the one particular vibration becomes amplified. Eventually, the whole bridge collapsed. But in that case, there was a record. There's a visual record of that particular collapse. That is a very famous movie. You may be able to get it from the internet. It's called the Tacoma Bridge. So the engineers in constructing anything had to estimate for every mode of vibration the natural frequency, and then try to do it in such a manner that any external forced vibration of frequency would not be close to any of the natural frequencies, to avoid the disaster. So far, at this point, we have a complex solution. But we can have two different complex solutions, and then you can combine them to make a real solution. So I will not go through that in detail, but you try to puzzle that out. But I want to change into a slightly different subject, and that is what happens if you have many degrees of freedom. What we had talked about is a one-dimensional problem. First, let's talk about the harmonic motion. Harmonic motion for small amplitudes. for discussing this, we go back to the equation of motion, but instead of talking about the equation of motion, we talk about the energy, total energy. Total energy is equal to kinetic energy plus potential energy. If you have several degrees of freedom, for example, you have a body like a molecule, it has several degrees of freedom. So the kinetic energy typically is like a summation of 1/2 mi xi dot squared, where xi, you have, for example, you have a molecule. Each molecule has a fixed position when it's not vibrating. Xi is now the deviation. Deviation from equilibrium position. For example, a water molecule consists of 1 oxygen and 2 hydrogens. Because of the force structure, it has a certain angle. So this is the position at rest. But when it starts to vibrate, each of them moves. So this one, so you have 3 xi's, which are the deviations of the oxygen from its rest position. And you have 3 for this, 3 for this. So you would have altogether, to start with, 9 x's. So you have x1 up to x9. Each of them is the deviation of that particular molecule from the original at rest position. So the kinetic energy is like that. The potential energy you expand into a power series of that x. So it's equal to a constant plus a linear term and a quadratic term. A linear term meaning it's proportional to x, quadratic term is proportional to x squared, plus a cubic term. The constant doesn't matter, or energies, because you usually take the derivative of the energy, so therefore that constant drops out. The linear term has to be 0, because if all the x's are equal to 0, it's like the bottom of the potential. So this term is equal to 0 because x I equal to 0 is the static situation. Does everybody understand what I'm talking about? Let's take a one-dimensional problem. We have a u. U is the potential energy, and we have a curve like this. And we are now talking about an equilibrium point. At the equilibrium point, the potential energy is a quadratic expression, no linear term. If it's at this point, there's a linear term. But that's not a point of equilibrium. At the point of equilibrium, the linear term always vanishes. So that's what I'm talking about, because that's why this is 0. So therefore, we only have a quadratic term. And these cubic terms for small vibrations are very small, so we also drop them. So the potential energy becomes essentially just a quadratic expression. In other words, the potential energy is equal to is equal to summation aij xi xj. That's a quadratic expression. A quadratic expression like this can be written as a matrix. It's x times the a times x. So let me summarize what I said. For a vibration of a molecule, in fact, it can be of a crystal, you have many coordinates. And the kinetic energy is a sum of xi dot squared with some coefficients proportional to the masses. The potential energy is essentially a quadratic expression which can be written in this form. So the potential energy is determined by a square matrix. That square matrix can be made symmetrical because x1, x2, and x2, x1 you can combine into one term and divide by 2. So therefore, A is real symmetrical. A real symmetrical matrix by a linear transformation can become diagonal. We have used that theorem. So that means if I change from the x, which is a series of x's, into x prime, so I write x as gamma times x prime. I transform x into x prime. Then in terms of x prime it becomes diagonal. In other words, the potential energy in x prime becomes omega 1 x1 squared plus omega 2 squared x2 squared, no cross term. And these omega 1, omega 2, omega 3 are the natural frequencies. So let me summarize what I just said. It's a fundamental idea. It's actually extremely simple. When you are near equilibrium, if you neglect triple cubic terms and high order terms, then the potential energy is quadratic. Any quadratic form can be diagonalized, and the diagonal coefficients are the natural frequencies. So when you have the Tacoma bridge has several motions. It can do this, it can do this, it can twist. So the engineers have certain approximations of a certain number of frequencies. I don't know how many. And they can calculate that matrix and can diagonalize it. So by computation, they can know the natural frequency. And the trick is to make that bridge such that the prevailing wind in that area would not generate a force frequency which is near any of those natural frequencies. What I just said in the last 10 minutes is a general principle. We know that all motions, when they are small, are likely to become almost likely to become damped simple harmonic motions. And with damped simple harmonic motions, there are two fundamental quantities. One is the damping term, the magnitude of the damping term. The other is the frequency. And that, in fact, applies to all motions. Okay, thank you.